Hello everyone, my name is Hamid Bejat and I will be presenting our proposed method for volumetric spatial smoothing of fMRI data. In particular, the idea here is that we want to perform an integrated brain structure function analysis on fMRI data. So if we are given some fMRI data, the idea here is that we want to perform spatial filtering of the fMRI data or the functional data in such a way that we can account for the underlying brain structure. Our specific goal is to design spatial filters that can adapt to the cortical morphology. As you can see here, for a given individual subject, we have a lot of morphological variability in the cortical structure, and the idea here is that we want to design filters that can account for this variability across the cerebral cortex. To do this, we will be using graph signal processing, which is a recently emerged field, which has attracted a lot of attention in the field. And it provides a unique set of tools for processing essentially brain functional data in such a way that the brain structure that can be accounted for. To do this, we need to first be able to represent our structure, basically our domain, our brain structure as in terms of a graph, where a graph is a structure consisting of a series of vertices and a series of edges, where the edges represent how these vertices are related to each other. And on this graph, we can also define graph signals, which for us will be fMRI data, as we will see. And these graph signals are essentially a vector of values that we are associating to the vertices of our graph. And the graph that we'll be using are cortical graphs, and they are voxel-wise cortical graphs. So each voxel within this representing the cerebral cortex becomes a vertex in our graph definition. And the definition of edges are based on two principles. In the first principle, we define the edges based on the adjacency of voxels in a cubic lattice of size 3 by 3 by 3. And in doing so, we can define how each voxel basically is connected or related to its surrounding voxels. And if we have our fMRI data that are co-registered to our functional data, our structural data, we can extract our graph signals, which can be visually represented as such, but in reality, in practice, this is just a vector of numbers. And the second principle that we will be using is to define our graph edges is that we will be pruning out those edges derived from the first principle that are anatomically invalid. In particular, we use the peel surface, and by using the peel surface, we can determine which of the edges that we have derived based on the first principle are anatomically invalid. For instance, as you can see here, all these edges that are shown here in the zoomed in section are invalid because they are passing through the peel surface in a narrow sulcus. And this happens because of the low resolution that we have in representing our brain structural data. So to be able to use principles from GSP, we need to have a spectral representation of our graph. And this can be done by transforming the representation that we have that is visual into a matrix representation to give us the adjacency matrix. And from the adjacency matrix, we can obtain the Laplacian matrix. And by performing the eigenvalue decomposition of the Laplacian matrix, we obtain a series of eigenvalues that fall within the range of 0 to a maximum value, which can be bounded by an upper range of 2 if we use a normalized Laplacian matrix. For instance, for the graphs that we are using in this work, we can see that the distribution of the eigenvalues are as such. So here we have 100 to 200,000 eigenvalues. And importantly, the eigenvectors together form an orthonormal basis that can represent any signal that is defined on these graphs. Here I'm visualizing some of these eigenvectors, which as you can see as I move above the spectrum, they entail more spatial variability, so representing higher frequencies. For the graphs that we have, the voxel-wise graphs, if you, for instance, we cannot compute all the eigenvectors, of course, because they're so large. But if we look at, like, for instance, the second eigenvector, which is the Fiedler vector, it looks like this, the third one, the fifth one, 10th, 15th, and so forth. And the idea here is that now if we have these eigenvectors and we have a graph signal, by computing the inner product between our signal and our graph, these eigenvectors, we can compute representation, so-called the graph Fourier transform of our signal, and as such, we can obtain a spectral domain representation of our signal. So again, for the large graphs that we're working on with here, we cannot compute this spectral representation at the resolution of the eigenvalues directly, and we also don't need it because we basically want to spatially process or spatially filter our graph signals. And to do so, we can use a suitable definition of a kernel. In particular, we are interested in low-pass filters, so we'll be using a heat kernel, which has a free parameter of tau. And the kernels, for instance, for different values of tau, they look like this. And for instance, if you want to see now how these kernels or how these filters look like, we can see that in the conventional setting, we use basically a Gaussian kernel, which no matter where you apply it, it looks the same around the red dot or around the blue dots that you can see, it always looks the same. But if we use a heat kernel defined on the spectrum of our voxelwise graphs, we can see that this kernel or this spatial function uniquely adapts to the place that is applied at. So you can see these here I'm showing at 8 regions, at 8 different regions. We can see that this kernel is uniquely adapting to the structure of the cerebral cortex around that area. So to validate the enhanced power provided by these spatial filters, we do simulation. First, we do a simulation analysis, and then we perform analysis on real experimental data. In the simulated data, we create synthetic activation patterns that follow the structure of the cerebral cortex, as can be seen here on one subject. And we repeat this procedure across 10 subjects. And basically, I'm showing the activation maps, the synthetic activation maps that have been created on top of a T1 weighted image. And then we add white Gaussian noise of different standard deviations to these synthetic signals. And first, we apply Gaussian spatial smoothing as a means to denoise the data in 2 settings, in an unconstrained Gaussian setting and in a constrained Gaussian setting. In an unconstrained Gaussian setting, the Gaussian kernels basically are not constrained in any way, but in the constrained setting, we confine the Gaussians to be just falling within the cerebral cortex, basically masking out regions that are outside the cerebral cortex, for instance, the CSF or the white matter. And we perform analysis across 4 different ranges of contrast to noise ratios. And as we can see, as we sweep across the full width half maximum parameter, what we are quantifying here, we are showing the area on the curve of the ROC curves of the denoising performance. And we can, for instance, here see that the constrained Gaussian outperforms the unconstrained Gaussian. But when comparing to the proposed graph-based spatial smoothing method, the free parameter that we have here is the tau parameter of the heat kernel. And we can obtain that for all CNR values, the contrast to noise ratio values, we obtain a superior performance compared to using either a constrained or an unconstrained Gaussian spatial smoothing. Finally, we explored the benefit of the proposed spatial smoothing using the proposed filters within the context of fMRI activation mapping on the Human Connectome project database, in particular 100 subjects, where for each subject we have 7 behavioral fMRI data for 7 different behavioral tasks. What we see here is the percentage of detections that are unique to data that have been spatially smoothed with the proposed method. In particular, we can see that approximately around 20% of the detections that we obtain using the proposed method are unique to this method and are not obtained on data that have been smoothed using Gaussian spatial smoothing. So each dot here represents one subject and each color represents one behavioral task. So backed up by the results that we obtain on the simulated data, this suggests that we are obtaining an enhanced sensitivity in detecting activations that are otherwise undetectable using Gaussian spatial smoothing. And on the other hand, if we look at the percentage of unique detections that are obtained using Gaussian spatial smoothing on data that have been spatially smoothed using Gaussian kernels, we again see that around 20 to 30% of the detections are unique to that method that are not detectable by our proposed method. And again, backed up by our simulated data, this suggests that we are obtaining an enhanced specificity in our detections. So these results are all obtained when using a heat kernel with a parameter of tau equal to 40. And so if we look at the black circles, that shows the mean across subjects for each of the behavioral tasks. And we do the same thing for the different other tau values that we have. Tau 30, 35, 40, 45, and 50, we see that the results are robust and replicate across different tau parameters. So this brings us to the end of this presentation, and I would like to take the opportunity to thank the funding bodies that have supported me and my research in the past few years. If you have any questions, feel free to reach out, and thank you very much for listening.